Elevators do not just lift you with brute force. That might sound strange, because when you step into an elevator, it feels like a machine is simply pulling a heavy box up and down a building. But modern elevators are much smarter than that. They use balance. They use counterweights. They use cables, motors, pulleys, brakes, sensors, and guide rails. And the big idea is simple. An elevator does not want to fight the full weight of the elevator car every time it moves. Instead, it uses a counterweight to make the job much easier. Think about a seesaw. If one side is much heavier than the other, it takes a lot of effort to move it. But if both sides are close to balanced, a small push can move the whole system. A traction elevator works in a similar way. On one side, you have the elevator car. That is the box people stand inside. On the other side, you have a heavy counterweight. Both are connected by strong steel cables that run over a wheel at the top of the elevator shaft. That wheel is called a sheave. The sheave is connected to an electric motor. When the motor turns the sheave, the cables move. When the elevator car goes up, the counterweight goes down. When the elevator car goes down, the counterweight goes up. So the motor is not always lifting the full weight of the elevator by itself. It is mostly moving a balance system. That is the main trick. The counterweight is usually designed to weigh about as much as the empty elevator car plus part of its rated load. In plain English, it is heavy enough to balance the elevator most of the time. If the elevator is empty, the counterweight may be heavier than the car. If the elevator is full of people, the car may be heavier than the counterweight. Either way, the motor only has to handle the difference between the two sides, plus friction and acceleration. That makes the elevator much more efficient. Imagine trying to lift a bucket of rocks straight up with your arms. That is hard. Now imagine the bucket is attached to a rope over a pulley, and the other side has another bucket that almost balances it. Now you do not need to lift the entire weight. You only need to overcome the difference. That is why elevators do not just lift you with brute force. They use balance to reduce the amount of work needed. This is also why elevators can move smoothly and quickly without needing a ridiculously huge motor. The motor still matters. It provides the force needed to move the system. But the counterweight makes the system practical. Without a counterweight, the motor would have to do much more work every time the elevator went up. That would waste energy, require bigger equipment, and make the system less efficient. Now let's talk about the cables. Elevator cables are not just random ropes. They are strong steel wire ropes designed to handle huge loads safely. Most elevators use multiple cables, not just one. That way, the load is shared. And the system has redundancy. Redundancy means there is more than one layer of safety. If one part has a problem, the whole system does not instantly fail. The cables wrap over the sheave at the top. The motor turns the sheave. Friction between the cables and the sheave helps move the elevator car and the counterweight. That is why this type is called a traction elevator. Traction means grip. The system depends on the cables gripping the sheave well enough to move the elevator. But the elevator also needs to stay lined up. That is where guide rails come in. Inside the elevator shaft, the car does not just float around freely. It rides along vertical rails. These rails keep the car moving straight up and down. They help prevent swaying. They also give safety systems something to grab onto in an emergency. So when you ride an elevator, you are not just inside a box hanging from cables. You are inside a guided machine moving through a carefully built vertical track. Now, one of the biggest questions people have is safety. What stops an elevator from falling? The answer is that elevators use several safety systems. First, there are brakes. When the elevator stops at a floor, brakes help hold it in place. The motor does not just keep fighting to hold the car there. A braking system locks things safely. Second, there are speed controls and sensors. The elevator system monitors movement, speed, door position, floor location, and other conditions. If something is wrong, the elevator can stop or refuse to move. Third, elevators have emergency safety devices. One famous safety idea is the elevator safety brake. If an elevator car were to move too fast, a governor system can trigger brakes that grip the guide rails. A governor is a device that detects overspeed. Overspeed means the elevator is moving faster than it should. If that happens, the safety system can activate and clamp the elevator to the rails. That is one reason modern elevators are much safer than people sometimes imagine. They are not just relying on one cable and hoping everything works. They are built with layers of safety. The doors are another important part. Elevator doors are not just there so people do not fall into the shaft. They are part of the control system. Most elevators have doors on the car and doors on the floor. The car doors travel with the elevator. The hallway doors stay at each floor. The elevator has to line up correctly before the doors open. That prevents the doors from opening when the car is not there. Sensors and interlocks help make sure the elevator does not move with doors open. An interlock is a safety device that prevents one action from happening unless another condition is safe. For example, the elevator should not move unless the doors are closed and locked. That is engineering safety. Not just making something move, but making sure it only moves when it should. Now let's think about energy. An elevator going up with people inside needs energy. The motor has to help lift the car. But when the elevator goes down with people inside, the car may be heavier than the counterweight. In that case, Gravity wants to pull the car downward. The motor may control the motion instead of simply lifting. Some modern elevators can even recover some energy through regenerative drives. That means some energy from movement can be converted back into electrical energy instead of being wasted as heat. So elevators are not just mechanical systems. They are also electrical and control systems. The motor, controller, sensors, buttons, displays, brakes, and doors all have to work together. When you press a button, you are not directly powering the motor. You are sending a request to the elevator control system. The controller decides which elevator should respond, where it should go, when it should stop, and how to move efficiently. In a tall building, this gets even more complicated. If there are multiple elevators, the system has to manage traffic. It has to decide which car should answer which call. It tries to reduce wait time, avoid unnecessary trips, and move people efficiently. That is why some buildings have different elevator groups. Some elevators may serve lower floors. Some may serve higher floors. Some may be express elevators that skip many floors. The taller the building, the more important elevator planning becomes. A skyscraper is not useful if people cannot move through it efficiently. Elevators are part of what makes tall buildings possible. Without elevators, very tall buildings would be impractical for daily use. Nobody wants to walk up 50 floors every morning. So elevators are not just a convenience. They are a major part of building design. They affect the structure, the layout, the floor plan, the mechanical systems, and how people move through the building. There are also different types of elevators. A traction elevator uses cables, a sheave, a motor, and a counterweight. This is common in taller buildings. A hydraulic elevator works differently. Instead of using cables and a counterweight, it uses fluid pressure to push a piston upward. That piston lifts the elevator car. Hydraulic elevators are often used in shorter buildings. They can be powerful, but they're usually not as efficient or practical for very tall buildings. So when people think of a classic elevator in a tall building, they're usually thinking of a traction elevator. That is the kind where the counterweight is doing a lot of the clever work. Now picture the whole system together. The elevator car sits inside the shaft. People step inside. Steel cables connect the car to a counterweight. Those cables pass over a sheave. An electric motor turns the sheave. Guide rails keep the car straight. Brakes hold the system when needed. Sensors track speed, position, doors, and safety conditions. The counterweight balances much of the load. And the controller tells the whole system when and where to move. The result feels simple. You press a button. The doors close. The car moves. The doors open. But behind that simple experience is a carefully balanced machine. The elevator is not just yanking you upward with brute force. It is using physics to make the job easier. It balances weight with a counterweight. It uses traction to move cables. It uses guide rails to control motion. It uses brakes and sensors for safety. It uses motors and controllers for smooth movement. That is why elevators are such a smart piece of engineering. They turn a difficult problem into a controlled system. Instead of asking a motor to lift a heavy box from scratch every time, the system balances the car against a counterweight. Then the motor only has to manage the difference. That saves energy, reduces stress, improves safety, and makes tall buildings usable. So the next time you step into an elevator, remember what is happening around you. You are not just inside a box going up. You are inside a balanced machine moving through a vertical transportation system. The motor helps move it. The counterweight helps balance it. The cables transfer the force. The brakes keep it safe. The rails guide the motion. And the whole system works together so you can move through a building with the push of a button. That is how elevators actually work.